Have you ever wondered how water moves invisibly beneath the Earth's surface, seemingly defying gravity in certain places? This fascinating movement is fundamentally governed by the interplay of hydraulic head and hydraulic gradient. At its core, hydraulic head represents the total energy an amount of groundwater possesses at a specific point. The hydraulic gradient, then, describes the rate and direction of change in this hydraulic head over a given distance. Together, they dictate precisely where and how fast groundwater will flow within an aquifer system. To understand this, let us break down hydraulic head. It is composed primarily of two energy components relevant to groundwater: the elevation head and the pressure head. Elevation head relates to the height of the water above a specific reference point, much like how high a reservoir sits. Pressure head, on the other hand, is the pressure exerted by the water due to its depth below the water table or within a confined aquifer. Groundwater always moves from a location of higher total hydraulic head to a location of lower total hydraulic head, seeking the path of least resistance and lower energy. The hydraulic gradient quantifies this energy difference over distance. Imagine measuring the hydraulic head at two different points in an aquifer. If there is a difference in head between these points, a gradient exists. This gradient, essentially a slope, drives the groundwater flow. A steeper gradient indicates a stronger driving force, meaning faster groundwater flow, while a flatter gradient suggests slower movement. This relationship is elegantly captured by Darcy's law, which states that the groundwater flow velocity is directly proportional to the hydraulic gradient and the aquifer's hydraulic conductivity. In practice, hydrogeologists determine hydraulic head by installing specialized wells called piezometers. These narrow tubes extend into the aquifer, allowing the water level inside to stabilize at a height directly corresponding to the hydraulic head at that depth. By measuring these water levels at multiple locations, we can then calculate the hydraulic gradient by simply dividing the difference in head by the distance between the measurement points. This calculation allows us to predict the direction and estimate the rate of groundwater movement. Visualizing this interaction is also crucial. Concepts like the phreatic surface, which is the water table in unconfined aquifers, and equipotential lines, which connect points of equal hydraulic head, become powerful tools. When you map these equipotential lines, you will notice that groundwater typically flows perpendicular to them, always downhill in terms of hydraulic head. Ultimately, grasping how hydraulic head and gradient interact provides a fundamental framework for comprehending groundwater dynamics. This understanding is indispensable for predicting the movement of contaminants, designing effective remediation strategies, and sustainably managing precious groundwater resources for communities and ecosystems worldwide.
If you love learning about water, like, subscribe, and keep exploring with us.